Now we are going to learn about a few propositions on the normal random variable, and these propositions are very important. Why? Because due to these propositions, we are just going to be able to calculate probabilities related to normal random variables. So it is therefore very important for us to understand these propositions and how they are going to help us, because in the end, we are going to learn calculating probabilities related to normal random variables. Even though the probability density function was too complex, in fact, the integral of that function is unsolvable, still, in the end of this chapter, you will realize that calculating probabilities related to normal random variables are just going to be very easy. But that requires the comprehension of these propositions. So the first proposition says that, let's just say, x is a normally distributed random variable, and it has the location parameter mu and the scale parameter sigma. So it is just any normal random variable with any location and scale parameter. Now I am just going to choose two real numbers, a and b. Any real numbers. It doesn't matter what I choose. And I'm just going to calculate ax plus b and define it as another random variable y. Now, if you remember, ax plus b was called a linear transformation of that random variable. And because x is a normal random variable here, y here is a linear transformation of a normal random variable. So basically, by multiplying a normal random variable with a and adding it to b, we are defining another random variable. And this proposition says that y here is also normally distributed with different location and scale parameter. So this proposition basically indicating that if you linearly transform a normal random variable, you will get another normal random variable with other parameter settings. So if you multiply a normal random variable with a and add it b, or in other words, if you calculate a linear function of it, if you linearly transform it, the output random variable will also be a normal random variable. The output random variables parameters will be different. So the location parameter of y will be equal to a mu plus b, and the scale parameter will just be equal to the absolute value of a sigma. So basically, y is going to be another normal random variable, but its location parameter will be a mu plus b, and its scale parameter will just be the absolute value of a sigma. Now, why we are using this absolute value? Because a can be any value. Here, if a is negative, the scale parameter cannot be negative, therefore we need to use the absolute value. However, here we do not use an absolute value. A can be negative, and the location parameter can become a negative value as well. So you see, according to this proposition, if you apply a linear transformation to a normal random variable, the output would also be a normal variable. However, the parameters of that normal random variable will be a mu plus b, the location parameter is this, and the scale parameter will be a sigma in absolute value. Now, of course, we need to prove that proposition if we want to really understand it, if this is true. The only way to prove that, actually, we need to show that this random variable y has the probability density function of a normal random variable with these parameters. So we need to determine the probability density function of y. Now, in order to determine the probability density function of y, we are going to determine its cumulative distribution function first, because if you have its cumulative distribution function, then you can take its first derivative to calculate the probability density function, if you remember. Now, we are just going to define the cumulative distribution function of y as capital Fy to indicate that this CDF belongs to random variable y. And that CDF will represent the probability of y being less than or equal to x. Now, in order to make this proof, first we are going to assume that the multiplier term of capital X is a positive value. And we can repeat the same proof for a negative multiplier A as well, but it is not necessary because the proof is just going to be very similar, only with a few changes. Therefore, at this point, we are just going to assume that A is positive. And since we would like to determine the CDF of Y, which is the probability of Y to be less than or equal to any X value, we can just write the definition of Y here. Y is defined as the linear transformation of X. So that probability is actually the probability of AX plus B to be less than or equal to X. Now, you know, in this inequality, we can just leave capital X on the left-hand side and everything else on the right-hand side. Now, that plus B moves on the right-hand side as minus B, and the multiplier A can be taken in the denominator of the right-hand side. And because A is specifically chosen as a positive value, the inequality sign would not change. And if you do that, that probability will be what? That probability will just be the cumulative distribution function of random variable X, which is capital Fx of X minus B over A. So we are calculating the cumulative probability at X minus B over A, or the probability of this random variable to take any value up to this point, and that is the CDF of this random variable at X minus B over A. Okay. Now, the CDF of Y is actually equal to the CDF of X, however, not at the X value, at X minus B over A value. So if you are trying to calculate the probability of Y to be less than or equal to X, you need to calculate the probability of X to be less than or equal to X minus B over A. Now, if you want to calculate the PDF of Y, then you need to take the first derivative of the CDF of Y, which requires to take the first derivative of this final part of this equation, the CDF of X at X minus B over A. So if you take the CDF at X minus B over A, remember we need to apply the chain rule. The first derivative of the outer function is simply what? It is simply the PDF of X at X minus B over A. However, if you are taking the first derivative, you also need to take the first derivative of the interior function. So this is a joint function here. We have taken the first derivative of the outer function, and the inner function's first derivative must also be calculated, and we need to multiply the outer first derivative with that, and the inner function is X minus B over A, the first derivative of which is equal to 1 over A. So the first derivative of the CDF of Y is the PDF of Y, which is also equal to 1 over A times the PDF of X at X minus B over A. All we need to do at this point is just to calculate the PDF of X at X minus B over A. Now remember, the PDF of a normal random variable was equal to 1 over sigma times square root of 2 pi, then e to the power minus X minus mu square divided by 2 sigma square. But because here the input is X minus B over A, in place of X, we are going to write X minus B over A. And because we have a coefficient 1 over A here, we are going to write that 1 over A here. Now, if you play around with the numerator of the power of the exponential function, it will become as X minus A mu plus B to the power 2, and the A square component will be written in the denominator part. So by a little algebra here, the power of the exponential term can become X minus A mu plus B to the power 2 divided by 2A sigma square. Now, if you just check this function is also in the form of the probability density function of a normal random variable. However, instead of the location parameter mu, we have A mu plus B, and instead of the scale parameter sigma, we have A sigma. A sigma. Therefore, this probability density function here is the probability density function of a normal random variable with location parameter set as A mu plus B and the scale parameter set as A sigma. Now, this proof shows us if you apply a linear transformation to a normal random variable with multiplier A and the additive term B, the output random variable will also be normal with location parameter A mu plus B and scale parameter A sigma. assuming that A is positive. If A is negative, then in that proof here, you need to change this inequality sign if you want to solve it for capital X. And when you do that, you need to write 1 minus CDF here. And when you take the first derivative again, you are just going to get the same output here. The only thing here, A sigma will just be the absolute value of A sigma. Okay, so the proof is very similar when A is negative, and when A is 0, Y is just going to be equal to a constant value B. So the proof is unnecessary if A is equal to 0, because if you multiply X with 0, then it will just become 0. So this proof shows us that a normal random variable, when you apply a linear transformation, will again be another normal random variable, which indicates that the property of normal distribution is not affected by the linear transformation. The probabilistic properties of a normal random variable is not affected by the linear transformation. So normal random variables are convertible to each other with linear transformation. Again, they will be normal. So that proposition was a good proposition. The second proposition here is just going to complete the first proposition, and it is just going to show us very genius and a helpful way to calculate probabilities related to any normal random variable. It says, if X is normally distributed with location parameter mu and scale parameter sigma. Again, X is just any normal random variable with any choice of the location parameter and any positive choice of the scale parameter. Now, if you apply such a transformation, which means from the normal random variable, you are subtracting its own location parameter mu, and you are dividing this difference to its own scale parameter. And you are defining this transformation as Z. Now it says Z is also a normal random variable, of course, because according to the previous proposition, if you apply a linear transformation to a normal random variable, you will also get a normal random variable, right? And this is just a linear transformation as well. Now, if you are careful, in this linear transformation, the multiplier term is equal to 1 over sigma, and the additive term B is equal to minus mu over sigma. So this is also a linear transformation. Therefore, here Z should also be a normal random variable. But this proposition indicates that Z is a standard normal random variable. So this proposition says that if you subtract the location parameter of a normal random variable from itself and divide the difference to the scale parameter, that transformation will convert the variable into a standard normal random variable. Now, the proof is very easy to understand. Why? Because this is a linear transformation, and in this linear transformation, the multiplier term for the normal random variable is 1 over sigma, and the additive term B is minus mu over sigma. And according to the previous proposition, after the linear transformation, the location parameter is calculated as A mu plus B. So let's do that. A is 1 over sigma and B is minus mu over sigma. So the location parameter of the new random variable Z will just be equal to 0. And the scale parameter of the new random variable after the linear transformation is absolute value of A sigma. And because A is 1 over sigma is multiplied with sigma, and we get 1. So the output random variable Z here is a standard normal random variable with location parameter equal to 0 and scale parameter equal to 1. And this transformation is called standardization. So for a normal random variable, if you subtract the location parameter from that and divide that difference to its own scale parameter, that transformation will standardize that normal random variable and make it a standard normal random variable. So this spatial linear transformation is called the standardization. According to the results of propositions 1 and 2, the normal random variables do not lose their probabilistic properties under linear transformation. So if you apply a linear transformation or linear function to a normal random variable, the output variable will still be normal. And let's just say for any normal random variable with location parameter mu and scale parameter sigma, we are interested in calculating the CDF, f of x, which is the probability of that normal random variable to be less than or equal to any arbitrary value of lowercase x. Now, in order to calculate this probability, let's just say we have applied the following transformation. So we are interested in the CDF value of that normal random variable with any choice of parameters. The probability of that random variable to be less than or equal to x is needed to be calculated. Now we are just going to apply a linear transformation on the both parts of this inequality. Because if you apply a linear transformation on both parts, the solution set of this inequality will not be affected. So what I'm going to do is this. I'm just going to subtract the location parameter of this normal random variable from both sides and divide the differences to the scale parameter, and the solution set of this inequality and the solution set of this inequality are just going to be the same. Therefore, if the solution sets are the same, the probabilities should be the same. Now, the left-hand side of this inequality is what? It is just a standard normal random variable, right? Because you have linearly transformed a normal random variable by subtracting its own location parameter from that and dividing the difference to its own scale parameter, and that makes the left-hand side of this inequality equivalent to the standard normal random variable z. And the right-hand side will again be linearly transformed. And that is the probability of a standard normal random variable less than or equal to lowercase x minus mu over sigma, which is the cumulative distribution function of a standard normal random variable at x minus mu over sigma. So you see, the CDF of any normal random variable with location parameter mu and scale parameter sigma is equal to the CDF of a standard normal random variable at x minus mu over sigma. So this is a very good thing, because for any parameter setting of a normal random variable, the CDF value can always be calculated by using the CDF of a standard normal random variable. So this means if we can just find a way to calculate the probabilities related to a standard normal random variable, then we can calculate the probabilities related to any normal random variable by using the linear transformation idea. So we are just going to use a numerical method and identify the approximate cumulative distribution function values for a standard normal random variable. And we are just going to store these values in a very large table. And if somebody asks us a question related to a standard normal random variable, we are just going to search this probability from that table and answer the question. If that somebody asks us a probability question related to a non-standard normal random variable, we are just going to apply this linear transformation. Again, we will convert the question into a standard normal random variable question and answer the probability again by using this table.